Hello, welcome everyone to this webinar, which is entitled The Facts About Compression Set. Here's just a picture of me so you can all visualize what I look like. So like I say, I'm a materials, like you can probably see in the bio and materials scientist here at PPE, Precision Polymer Engineering. My focus is primarily the oil and gas business line, so focusing on those customers, giving them support and driving our developments in that business line. So I'll just take you through the agenda for today. What we're going to cover over the next. Well, I'm aiming to speak for about half an hour to give plenty of time for questions at the end. So we're first going to look at what exactly is compression set. How do we measure it? Why is it important? We'll then move on to address some of the potential issues and sort of pitfalls that can arise from using this method, and shall we say maybe poor application of the results. We'll then move on to look at a related test method called Compressive Stress Relaxation, or CSR. We'll look at how that is measured, and take a look at maybe some of the benefits that this may have over the more standard, more widely used compression set testing. And then we'll then take a look at how, what implications the results and the test methods could have for yourselves as seal users. So what is compression set? So we've just included a micrograph here, which is a seal that's kind of taken on sort of classic compression set. So this was at one point an O-ring, so it was round in shape. It's been placed in application, and after this application, it now no longer recovers its full round shape. So compression set, the visual indications. So the cross-section of the O-ring is no longer circular. So flattened surfaces have taken on the shape of the groove. So the O-ring, or indeed any elastomeric part, has taken on set. So it now no longer recovers or returns to its original shape as a result of the elasticity in the system. It now has a shape that's more similar to the groove in which it was placed, or indeed any hardware in which it was placed. So the set is quantified as the percentage loss in compression when we compare to the original compression applied. So let's kind of delve a little bit deeper into exactly what we mean when we say compression set. So it's often when people are referring to compression set or compression set testing, they mean the test method as outlined by STM D395. This is very similar to ISO 815. I'll touch on some of the differences between the two methods, but for the most part, when people refer to compression set testing, they're referring to the testing as outlined by STM D395. So what is this test method? How is it? How do you apply it? So what we're looking at is the recovered height of an elastomer sample, often a button, but could be an O-ring or any kind of sample. So we're looking at the recovered height of this sample after the application of a strain. Now, most of the time, pretty much always, this strain is applied by a 25% deflection. So you'll see in the slide I've got up now, there is a typical compression set jig, as we'd call it. So a set of buttons have been placed in between those two metal plates. The whole thing's been bolted shut. There are metal spacers in there, and they are of a height such that the buttons that have been placed between the two metal plates are subjected to a 25% deflection. The method, I'll just mention it for completeness, but this test method is very rarely employed. But it's also possible to get to this strain through the application of a constant force, but that is very, very rarely applied. So kind of just also on this slide is a sort of schematic of button inside the test jig there. So as you can see, the button is placed between those two sheets, compressed by 25%, and then if I just move on to the next slide. So what we do is, so it's compressed by 25%, and then after some time later, often in an elevated temperature environment, often placed inside an oven, the jig is taken apart, and we look at the amount of recovery that happens. So compression set is calculated as on this slide. So it's the initial thickness minus the recovered thickness divided by the initial thickness minus the compressed thickness times by 100 to give us a percentage. So what we're looking at here is the amount of recovery. So slightly counterintuitive, but 0% compression set means complete recovery, and 100% compression set means no recovery at all. We've kind of done a simple example here that comes out to a nice round number. So if we took a 10 mil button, we compressed it by 25%, so we'd compress that down to 7.5. If when we took it out and measured it again, it was 9.5 high, any unit, but often this would be millimeters, you'd have a 20% compression set there. So shown slightly more visually on the next slide, you can see that after that button comes out, we'd have an 80% recovery, a 20% non-recovery, so a compression set of 20%. The next slide goes into slightly more detail about exactly how and when you have to make all these measurements. So you'd measure the height of the O-ring or the sample before it's tested. You'd place your jig on the strain, so you'd assemble your jig, strain your sample, and place it in an oven for a given time and temperature. We'll touch on what kind of times and temperatures are often employed in a little while. You then remove your jig from the oven or take it out of wherever it's been held at, say, room temperature. You disassemble the jig. You allow the O-ring to recover for 30 minutes, or sample to recover for 30 minutes, and you measure the height. And then you apply the formula as in the previous slide. So the above is as per ACM D395 method B, and it's one of the two allowable methods in ISO 815. ISO 815 also has a secondary method in which the O-ring is allowed to cool in the jig. However, this introduces significant amount of what's termed, well, what we often term cold set. Exactly what cold set is, I will address in some detail in later slides. So let's just park that thought for a minute and take a look at some sort of typical compression set results. So compression set is a value that we'll often see listed on data sheets. So here's our Endura V91J data sheet, and we list a compression set after 24 hours at 200 degrees C, as per the test methods outlined, of 24%. And a couple of screen grabs taken from a little bits cut from other data sheets of ours. Here we've got a material that was after the same time and temperature 19%, and another material after a slightly lower temperature of around about 20%. So, you know, what kind of information can we get from this? Which one of these materials is best? That's the kind of questions that we're going to try and address over the remainder of this webinar. So, kind of this just gives you kind of an idea of the times and temps that are often used. So EPDMs, if you look at the majority of EPDM data sheets, EPDM being a type of base polymer from which elastomers are based, you'll often see, say, 125 degrees C in 24 hours, and then NBRs, 100 degrees C, 24 hours is very typical. HMBRs, FKMs and FFKMs. So you can see there some typical times and temperatures you'll often see on data sheets of these types of base polymer elastomers. And the question is, how do we compare one, or can we compare one material type against another? How much information can we derive from this single data point given on a data sheet? So to kind of illustrate that point further, so here are some questions that we should be considering about compression set, and hopefully at the end of this webinar you'll be able to answer some of these questions, or at least give these questions some real serious thought when selecting materials and when designing with elastomeric materials. So, compression set, does it help me predict my seal life? Will it give me an indication of the sealing efficiency? Is it what difference between compression set values is significant? And am I able to relate this to my actual application conditions? So why is compression set important? Well, a reduction in a cross-section will, or the introduction of set will result in a lower contact sealing force between your sealing material and the hardware. So this will increase the risk of leakage. This is because the formation of a seal requires a reaction force between the hardware and the seal, particularly when we're trying to form a seal. So when upon the application of pressure, some degree of reaction force between your sealing material and hardware is required. We often refer to this as the initial sealing force. So compression set, though, the compression set over time is believed to give an insight into the reaction force and the reduction in sealing efficiency as time progresses. So again, let's look at maybe two points we might have gleaned from a data sheet. So here are two materials. We've tested them at 200 degrees C for 24 hours, and we've got two sets of compression set results. Which one of these two materials is best, or would be superior? Well, perhaps you might think, well, the one with the lowest number is the best one, the one to go with. However, perhaps it's the case that the evolution, or the way that the compression set progresses as we measure it, looks like this. So now you might say, well, after 72 hours, the condition is flipped, and I think it's a really important consideration when looking at compression set numbers and looking at how the reaction force progresses, that we see how the property evolves over time. To that end, let's look at some typical results. So here we have results from 4 families of elastomers: HMBRs, FKMs, FEPMs. These are often referred to by their trade name of Atlas, and an FFKM there. So, the first sort of more general point to consider here is that you can see that in most cases we have a rapid increase in compression set initially, but all these curves sort of begin to plateau. This is true kind of across the board here. There's a couple of things I'd like to draw your attention to. The first is the HNBR results at 200 degrees C, which are the green triangles that we've circled there on the HNBR curve there, top left. Now, HNBRs are typically given an upper operating limit of about 175 degrees C, so the testing here would be considered to be above the maximum operating limit of this material. As you can see, this is kind of reflected in the compression set results returned. There is no plateau. There's just a very rapid, continual degradation in the compression set results, and that's kind of giving you an indication for one of the reasons, or one of the multitude of reasons that might go into defining the upper operating limit of a material. So the other thing as we move around, you'll see you've got FKM and FFKM. So you might say an FKM upper operating limit of 200 degrees C, and FFKM is around 250. And the evolution of those curves maybe gives you some insight as to how those numbers are reached and why, and more information as to why a FFKM is considered to be more thermally stable than an FKM, and then the FKM in turn to the HNBR. FEPM is a kind of interesting case. Again, there's a little circle there on that curve where we can see that the compression set has quite rapidly, after just 24 hours, reached round about 40%. However, then these curves quickly plateau, and the behaviour is very similar to that of, say, an FKM for longer time periods. And this is just to illustrate the fact that on the first glance at short-term compression set testing, an AFLAS or FEPM type material might appear to be much worse than, say, an FKM, with results of 40% when we compare it to, say, 20% or even 10% for certain specially designed low compression set FKMs. However, these types of materials are widely used across a number of applications. So, it's important to consider, as I say, the full evolution of your compression set results over time, rather than just considering the single data point that may be given on a data sheet. So let's move on to sort of maybe attempt to give an explanation for why the AFLAS FEPM type materials do jump so quickly up to around this 40% mark. We do this by considering some of the issues with the test method, and the main issue is a phenomenon called cold set. So when we measure a compression set, it will have two components. The first, the first thing that prevents the seal, and the most damaging or worrying thing that would prevent a seal from recovering, would be the formation of new crosslinks between polymer chains in the compressed position. So the action of chemicals and heat and so on and so forth has resulted in new crosslinks forming in the compressed state. These then prevent full recovery of the seal, and these are permanent, non-reversible reactions. Another thing we might be observing is the fact that under high temperatures, so elastomers are very, very, you can imagine them, that the polymer chains are a little bit like a big bowl of spaghetti. And all these long chains, yes, they're joined together, but there is some degree of movement that is possible. So at higher temperatures, more movement is possible. So while stressed and while compressed, the seal is trying its best to minimize the stresses that it's experiencing. So these chains kind of orientate themselves as much as possible to reduce these stresses. Excuse me. So at higher temperatures, such as test temperatures, there is much more chain movement that is possible, because the system energy is significantly higher than at room temperature. However, when the seal is then cooled, these chain movements now no longer have the energy to relax themselves and to reverse, and they get almost locked in. So this kind of locking in of stresses introduced under high pressures is often referred to as cold set. Some of you also might have heard it referred to as, say, the Monday morning effect, where machinery that's been shut down over the weekend and cooled down over the weekend then leaks or weeps slightly when it's turned back on Monday, until the whole thing warms up again, and all the seals that are there now have the energy to start moving and start reacting to the applied pressures and forces and so on and so forth. So maybe to give this a little bit of an example, let's consider an experiment that we ran to kind of demonstrate this cold set phenomenon. So what we did was we took one sample, and we placed it in a compression set jig. We took the jig to 150 degrees C. We removed this jig from the oven warm. We took it apart. We measured compression set in the normal manner, returning a result of 3%. So very minimal, compression set, as maybe expected after such a short exposure at 150. We then placed the button that was displaying just this 3% set. We warmed it in an oven back at 150, and we measured the set again after warming it for just 30 minutes in an oven at 150. And there was pretty much no set observed, just 1% set. So there was very little set observed in this button, even straight from the oven, but almost none observed after we'd warmed it unconstrained. We took a similar button, placed it in between a compression set jig, put this in the oven at 150, and then we took this out and allowed the entire jig to cool to ambient conditions before removing the button and measuring compression set in the normal way as outlined before. Now, we measured a pretty high result of 44% after 30 minutes in this button that had been allowed to cool while constrained in the jig. However, once we placed this button in an oven and warmed it for just 30 minutes at 150, we found pretty much full recovery. There was no set observed. So this really illustrates the fact that allowing that O-rings or any kind of elastomer seal that's allowed to cool in situ, when you take it out, there's a high probability that if you do observe set, if they do appear flat, and some of the set observed is this so-called cold set. So often, I do a lot of failure analysis work, looking at seals that have failed in application, and often people will send back seals that may not have failed, but they've pulled them out and they look flat and they think they've taken on set and there's an issue. The first thing I'd do with these seals is place them in an oven and see how much recovery we get on warming. So how much of the set observed we can attribute to reversible chain movements that have happened at elevated temperatures, as opposed to permanent formation of new crosslinks that are irreversible. So, what are these causes of compression set? Here we're talking about the permanent formation of new crosslinks, and we'll refer to this as compression set. So chemical attack will increase the crosslink density, so the O-ring begins to lose its elasticity and it won't return to its shape. Elevated temperatures introduce these stresses in the O-ring. They're unable to relax out when the temperature is reduced. So this is the cold set, but this is completely reversible on heating. So when you see a compressed O-ring, you need to always be asking yourself the question, is this permanent introduction of new crosslinks, or is this a reversible cold set effect that if I place it in an oven for a short period of time would spring back? There's other things that can happen that can contribute to compression set or increased amounts of compression set. The first is improper groove or gland design. If you overstress an O-ring, for example, while it's in the groove, you'll get increased amounts of observed compression set. The same with volume swell. So if there's been significant amounts of volume swell, ingress of fluid during the application, this will lead to compression set. And the real, which we obviously would very rarely see, but this would be the incomplete curing of the seal during production. If a seal was not properly cured or hadn't been produced properly, there was a quality issue there. Clearly, not clearly, but residual cross-linking agents that should have been in the normal production cycle been used to create crosslinks, beneficial crosslinks that would introduce elasticity, have not been. This has not happened, and they are then able to go on and make crosslinks in the compressed state and actually prevent full recovery and full elasticity. So we move on to a slightly sort of related but different test method, which is CSR. So as we've touched on, when compressed, an elastomer generates a reaction force or a sealing force. So if you look at the first the first picture there on the diagram, you can see that this sealing force is quite large, and we've called it F0. Over time, the sealing force, or the force that is returned by this seal, will decrease. This is known as compressive stress relaxation. So you can see we're moving forward in time from left to right there, and the force is slowly but surely decreasing. So CSR is accelerated by exposure to chemicals or elevated temperatures, so they interact with the polymer backbone and the cross-linking system. So what's happening here is new cross-links are forming. They are preventing or reducing the force being exerted by the seal, and the force is reducing as observed. So how do we measure it? So a standard test piece is again compressed between two flat sheets to often 25%, and the force exerted by this test piece at specific intervals is then measured. So this can either be continual. So the top picture there shows continuous CSR equipment. So there you've got two metal plates directly attached to a force meter and height gauge, and that height gauge, and that goes straight to a computer, which is very regularly taking a recording of the force being returned by that O-ring sample or button sample or whatever it may be. The other thing would be non-continuous CSR. So you have small CSR jigs, which are placed much like compression set jigs into ovens or into test fluids or whatever that may be. And then periodically that jig is removed, placed in between a machine which is able to tell you the current force being returned by the sample. You're then able to plot that against time. So the results are often expressed as a percentage against, but this percentage would be the current force being returned divided by the force, by the original force, and then expressed as a percentage. These CSR tests are again have standards that govern how you should carry them out, and they are ASTM 6147 and ISO 3384. So here we have some typical results from CSR. So here we can see the FEPM type material in this test is arguably the best performer. It is retaining its seal force much better than the other three materials, which are FKM. So we've got a couple of turf polymers and an FKM copolymer. Now, if you think back to the results originally shown in compression set testing, particularly over shorter time periods, FKM type materials are often held to be better in compression set than newer AFLAS materials. But now, if we come and think about the CSR testing, the results are kind of flipped. Now, why might this be? We suggest that this is kind of reflected in sort of cold set type effects. Now, one of the other drawbacks of AFLAS type materials, or these FEPM materials, is that they have high glass transitions. Now, a glass transition is in effect a reflection of how mobile the polymer chains within the elastomer are. So a higher glass transition, so just to touch on exactly what we mean by glass transition, the easiest thing, we've probably all seen the experiment of, say, a flower or a banana or whatever it may be that gets plunged into liquid nitrogen, and we pull it out and we're able to shatter the whole thing with a hammer. Exactly the same thing happens to elastomeric samples. When they get cold enough, they are no longer elastomeric but become glassy and brittle. The point at which this happens is often reflected by the TG. And what we're essentially seeing here is the point at which those chains are no longer able to have significant amounts of movement. The system energy no longer allows them to freely move and rotate. And so sort of a higher TG would be an indication of a higher or a reduced polymer movement. So this high TG of AFLAS-type materials could be considered or could be believed to introduce more cold set effects. An AFLAS-type material is less able to relax out the stresses introduced while compressed. And this is reflected in compression set testing. So while we're allowing those samples to recover at room temperature, the AFLAS-type material quite quickly doesn't have the energy required to relax out all those movements introduced at high temperatures, whereas the lower TG FKMs and so on and so forth are more able to carry out this relaxation at the lower non-test temperatures. However, when we're looking at CSR and all of our measurements are carried out at the test temperature and the temperature of interest, we get a far better indication of how the sealing force is decaying, and we remove the potential for our results being influenced by so-called cold set. And the final point that I'd like to touch on would be the fact that the vast majority of compression set testing is carried out in air. Now, clearly, most applications are not in pure air; they're in various other things. So, a customer of ours requested that we carry out compression set testing not in air, but in a fairly in what was believed to be a fairly aggressive sour gas environment. So we placed exactly the same jigs as previously, or the same design, perhaps not the same metals, but the same design type jigs were placed in a vessel that contained 10% water, 60% hydrocarbon phase, which consisted of methane, 25% H2S and CO2, and so that would be the gas phase, and then a hydrocarbon phase containing heptane, cyclohexane, and toluene. So here we have a very, what may on first glance appear to be a very aggressive cocktail of fluids containing aromatics, containing hydrogen sulfide, containing CO2, and then these then went in an oven, or it were then heated to 100 degrees C for 72 hours. Move on to the next slide. However, the test method requires that you pull these samples out at the test temperature, disassemble the jig, and then carry out your measurements. However, safety concerns meant that it wasn't possible to take these jigs out at the test temperature. You had to allow the vessels in which this testing had been carried out to come down to room temperature before we were able to disassemble the jigs and carry out our measurements. So what we wanted to do was avoid any sort of cold set effects. So what we did was we warmed the samples for 30 minutes back at the test temperature before removing them from the oven, allowing the usual 30-minute recovery time. The result obtained was just 4%. Now this was almost perceived to be too good by our customer. So what we did was we, due to this deviation from the standard method, that is the cooling and then warming unconstrained and then carrying out the measurements, we had to validate this deviation and see how much effect it would have on the results. So we did a compression set in air, as you might normally do, by the normal method, 72 hours or 100 degrees C, and returned the result of 14%. We did compression set in air, allowed the jigs to cool to ambient, then disassembled them, and we had a result of 21%. So there you can see the influence of cold set there, making the result slightly worse. We then kind of replicated what had been done in this aggressive sour fluid. So we did it 72 hours in air, allowed the jigs to cool in ambient, took the buttons out unconstrained, warmed them for 100 degrees C, and then for 2 hours, and we got a result of 12%. So what we've demonstrated here, that actually that kind of additional step is very, very similar to the result returned by the normal method, and also that it is required to prevent the cold set effects influencing the result. So here we can see the material perform better in compression set testing in a sour fluid than it did in air. Now, this at first glance might seem strange or slightly odd, but I think what this demonstrates is that what may be considered to be an aggressive fluid when we might consider it, to certain elastomeric materials such as the FKM tested here, the presence of the oxygen in the air when doing elevated compression set testing is more detrimental and reduces that returned force more rapidly and more aggressively than aromatic fluids and sour fluids. So let's move on to some of the conclusions that we hopefully draw. Compression set, like I say, it's often measured under laboratory conditions, constant temperature in air. So this can make application to the real world difficult. The other thing that we'd like to emphasize is that to really understand the behavior of a material, we really need to consider how this behavior evolves over time. So we really need to test our materials for long enough that the trends develop. A few days here and there might not be enough to really see how the trends develop, to see the plateau points, to see whether we just get straight lines or we do indeed get plateauing results. As I think we've touched on here, the measured compression set has two components: permanent formation of new bonds, which is irreversible and will always prevent the full recovery of the sample, and reversible bond movements, which will relax out on heating. The CSR type testing could give better insights as cold set effects are minimized. So like we said, so care must be taken to properly assess the testing results, and really consider the full, make sure we've got a full picture before selecting our seals and assessing our compounds. And I suppose the point we'd say here was talk to your seal supplier to make sure that you really have all the data required to make these type of seal selection and compound selection decisions. And I'd always say for the most critical applications, we'd always suggest that a bespoke testing regime is carried out. That, for example, exactly as the customer did it just a few slides ago, suggested that rather than just air, we carried out some testing in a more applicable fluid. So I suppose if you return to the FAQs about compression set, do we think that the compression set numbers can help predict seal life? Well, almost certainly in certain situations if applied properly. And the same will be true as how does this give me an indication of sealing efficiency. We need to make sure that the numbers that we're looking at are properly and prudently applied to our application. So finally, is the difference of 2% between materials significant? I mean, we're measuring height and things here. I would I would often say that the be-all and end-all isn't just a slight difference in a one-off test, but what we really need to be considering is the longer term evolution and how these materials holistically perform, as opposed to just focusing on one property and maybe small differences between that. And I suppose the final point would be how does compression set value relate to my application? I think what we've really tried to illustrate here is that real care needs to be taken when applying compression set values from data sheets to real-world application conditions. So thank you everyone for your attention today, and now we've got a little bit of time for questions.
Okay, thanks Matt for your insight into compression set. Now let's get the Q&A underway. We have about 20 minutes for questions, so we'll kick off with our first question. Okay, so first question, Matt, is can I just squeeze the seal a bit more to compensate for compression set?
I think we touched on this slightly in the slides, but in the short term, yes, people do this for short-term applications where they're worried about very short-term excursions to high temperatures, but the compression set will always be progressing over time. So eventually, this increased squeeze will be overcome by the compression set, and you will still potentially have a failure through that. The other thing worth mentioning is that over-compressing a seal, as I might have said, over-compressing a seal, applying too much squeeze to a seal, can actually exacerbate and worsen the amount of set that's observed.
Okay, thanks Matt. So here's our next question. Why is compression set shown on data sheets if it's not so relevant?
I think care must be taken when completely dismissing information that's widely given on data sheets. It's very, very relevant as given say a first pass. What I often say around compression set is take FKM for example. The vast majority of FKM materials are tested at 200 degrees C for 24 hours or 22 hours. And then the numbers are there available for people to review, and for a first pass you can compare, make sure you're there comparing apples with apples as opposed to apples with oranges. But the other thing to say is if you suddenly come across to say an FKM or such like that's been tested at say 150 degrees C and is returning a similar result to those tested at 200, and it's sort of a non-standard temperature for the industry, then it can give you pause to sort of consider why there's this discrepancy and just probe that. And there may be very good reasons for why that's the number that's been chosen to be displayed, but it can give you a reason just to probe a little bit deeper. But I'm not saying it's completely irrelevant. It's a good starting point, and clearly it's impractical to sort of have reams and reams and pages of compression set data just being on a data sheet. That we need to start somewhere.
Okay, thanks Matt. How does EPDM compression set or CSR compare to others such as FKM?
Yes, so I tried to sort of show in if we can find the slide in the data. EPDM is kind of similar to say an HMBR. So it has a very, very similar kind of behavior in that within the temperature range over which it operates and has been shown to operate well, you'll get that kind of very classical, but that kind of initial increase, and then it will plateau at some points. But what happens is the less thermally stable materials such as EPDMs, the point at which you get a rapid degradation in compression set, or the plateau begins to settle out significantly higher than, say, a more thermally stable material such as FKM or indeed FFKM, and that's kind of demonstrated in that slide. So if you take a look at, say, I mean, the easiest thing would be to compare, say, for sake of argument, we could consider the HMBR results to be very similar to EPDMs in terms of their upper operating limit and so on and so forth. So if we look at, say, 100 degrees C, pretty much across the board there, we're seeing that you're getting a nice plateau. You're getting a nice plateau at, after a few days, and it's not really approaching 100% at 50 or 60%. Pretty much across the board, even HMBRs to FKMs to FFKMs. As we move to the more thermally stable FKMs, for example, at 150, there we are. We're seeing the plateau being much lower for FKMs versus HMBRs, and for HMBRs, really PDMs. And then if we then move on one step again to the FFKM, there you can see even at 150 degrees C, we're getting a very nice plateau at these lower temperatures for this more thermally stable material, and then moving up and up faster for those less thermally stable materials.
Okay, so we've got time for just one or two more questions. So, does pressure affect compression set, and if so, how?
Compression set will be affected to an extent by pressure. So pressure can increase. The main thing that happens with pressure. Is that the stresses imparted will be higher, so there'll be an increased amount of set through that, and pressure can to an extent increase the rate of reactions by increasing concentrations and so on and so forth inside the elastomers. I think the key thing that pressure does is pressure really comes on and is there to form seals and to be the force against which the seal reacts.
Okay, thanks, Matt. So this is our last question for this session. How do I prevent compression set from occurring?
Well, I mean, I think the simple answer to that is you can't. So it will happen when you subject seal materials to elevated temperatures and certain chemicals and so on and so forth. I think the key is to understand how your seal will react to compression set, how the behavior will evolve over time, such that you can be sure that the material that you're selecting will not, the steel that you're selecting will not fail before the required lifetime through compression set.
Okay, thanks, Matt. So we're going to have to wrap up the webinar now. So to find out more about compression set, or if you have any other questions that you want Matt to answer, please get in touch. His details are on the slide now. Or failing that, you could go to the PPE website and have a look around there as well. So thanks everybody for taking the time to learn about elastomer seals and how PPE's solution-minded approach can help you achieve the results that you need for your high-performance sealing applications. Thanks very much and have a great day.